Yeah, so I'm going to talk to you about something that's actually quite old, but has only been recently rediscovered, the so-called Halidperowskites, and how they're potentially promising to revolutionize what we're doing in terms of solar technologies and other optoelectronic applications. So, if this works, which it, oh, here we go. Okay, just a little bit slow, I guess. All right. So sorry about the color scheme, looks a little bit crazy, but basically, so one of the big problems that's troubling the world today is energy, obviously, as you know. And this little circle here represents the global energy consumption, essentially what the world uses, which is about 16 terawatt years per year. If you compare that then to the reserves that we have, I don't know why this doesn't keep switching. All right, I'll just do it like this. All right, if you compare that to the reserves that you have there, you see that at least a number of these fossil fuel elements, coal, uranium, oil, we still have substantial reserves, although if you compare it, for example, to natural gas, you see that something on the order of only about 15 years possibly left over to sustain the maximum energy. So obviously people have now turned to renewable energies, and you can see the sort of scale that they're able to produce each year. So some of these minor ones, tidal, geothermal, and hydro, basically are not comparable really to what we need to produce ocean thermal wind power, which is actually one of the most productive. There actually has quite a lot of potential, but obviously it doesn't work when the wind's not blowing. But if you compare this essentially to one of the sources that we have here that we're not really using, which is the sun, and you'll see that essentially none of these technologies necessarily really needs to matter. So all we need to do is capture all the, or a small part of the light that actually is shining onto the Earth and use that then to easily sustain the global energy demands. And so just to look at what that might look like if you needed to capture all of this, so this is actually an older slide where basically the efficiency of solar cells were actually quite low, so at 8%. If you covered an area on the Earth with the solar cells full of 8% efficiency, how large that area would be needed to cover the entire Earth, or to cover the entire Earth's global energy costs. And you can see that these are large spots, but technically, compared to the landmass of the Earth, really not anything particularly large. And so if you compare that then to the current usage of land, when you can see that there's a lot of land that's essentially not usable. Glaciers make up 10% of land, barren land, so deserts and salt flats or rocky domains, about 19%. 27% actually is used for livestock, so that means meat and dairy production, or for raising food for growing cattle, for example. Forests, 26% that are not really used. Fresh water itself, almost only a very, very small part. And the built-up area that we have currently, so that's all towns, cities, roads, airports, anything like that, infrastructure, only makes up about 1% of the total Earth's land mass. And so, just to point out, so essentially farming itself, the land that we're using for farming, takes up nearly about a third of all land area that we have on the planet. Okay, so then people came up with the idea, great, why don't we take some of this land that's not usable, for example here, this is the north part of the Sahara Desert, and try to cover that with solar cells. So these squares represent the area that you need to cover nowadays to be able to sustain the energy demands of the Earth. And you can also see that essentially they would nicely fit into the desert without really anybody noticing that they're actually there. There are two major problems though of putting solar cell parks in the desert. First of all, it gets very hot there, and solar cells don't work very well when it's hot. And the main problem is sand. So the sand gets blown about. Sometimes we even notice it here in Germany when it gets blown over, but essentially it would cover the solar cells and then render them nearly ineffective. So that's why they basically gave that idea. Okay, so could we do this in Germany? So where do we have the area to do this? Well, basically, you know that a number of years ago when we started up the renewable energy program, and people started building up solar cells like crazy, especially people in the south, in Bavaria. And so if you just take a look at the total roof space that we have available in all of Germany, you could actually produce about 161 gigawatts of energy if you covered all of them with solar cells. And current yearly production in Germany is about 81 gigawatts and all the other forms of energy. So essentially, we have twice the amount of space necessary even to cover all of the energy demands just by putting solar cells on the roofs on top of Germany without even having to build up any solar parks. Okay, so back to the history of solar cells. So they're actually not that old. 1954 was the first working solar cell. It's built by Bell Labs, and this is one of the first ones where they installed it on top of a telephone pole, and essentially they powered the telephone call using this solar cell. So back then, the efficiency was only about 6%. Nowadays, obviously, we've advanced quite a lot. So in the labs, the best silicon solar cells get up to 26.6%. These are only really tiny ones and not necessarily useful for anything. And typically, commercial cells are on the order of about 15 to 20%. So since then, since this first solar cell was built up, there's been a lot of solar built up over the entire world. Germany is one of the main leaders in that. Also, China now is picking up quite substantially now that they're realizing that pollution is not really so cool. And so currently, we have about 400 gigawatts of energy from solar panels installed over the entire world, which is actually quite remarkable. Okay, so the solar cell industry currently is dominated by silicon. Most of it is gone there. And essentially, it's all it is driven by price. All people care about is how expensive is energy. So essentially, the key number that they're looking to is the dollars per watt. And you can see that essentially it started up basically, this is in the 70s when they started bringing out the first commercial solar cells, around about $100 per watt, and it's gone down significantly. And now if you compare that essentially with installed power, you can obviously see an inverse trend. So the cheaper it becomes, the more power is installed. And so at the end of 2017, sorry, that was still in German, I didn't get all of it, we're down at a price then for the lowest cells of something about $0.33 per watt. So it's very, very competitive. And as you can see, then the installed power has shot up because now with government aid, and so it's been more attractive. And so it's been installed more and more worldwide. Okay. So typical solar cells rely on semiconductors such as silicon or gallium arsenide, cadmium telluride. Just to explain briefly how a solar cell works in case you're not familiar with that or it's been too long since you've done solid state physics. So essentially in a semiconductor we have a so-called band gap where electronic states don't exist. And that separates then the valence band, which is completely full of electrons, and the conduction band, which is top where they're essentially all empty states. And now if we bring in a photon that has an energy that can lift up an electron from the valence band into the conduction band. We then have obviously one state that's filled in the conduction band, and in the valence band one that's empty. And now these then can move along because essentially they can move through it, and that essentially creates charge transport. That's how a solar cell works. Okay. So I said we need a photon that has enough energy. If we have a photon that doesn't have enough energy to bridge the gap, obviously it's just going to travel through the solar cell and not be absorbed. So there's no absorption in that case. If we have a photon that has an energy that's far above it, it's going to bring the electrons into a state that's far above, and the charge carrier is then going to relax down to the edge of the band gap, of the valence band, and then still be able to do charge production. Okay, so the band gap is critical. So obviously, where is it in silicon? The band gap in silicon is about 1.1 electron volts. So that's far deep into the near infrared region. Oops, sorry. I messed that up a little bit. And if you compare that with the spectrum of light that's coming from the sun, you can see essentially this is the AM 1.5 spectrum. So essentially the amount of light that actually reaches Earth's surface. There's a lot absorbed by water and by clouds and other molecules that we have in the atmosphere. And you can see this is only the visible part. So this is all that we can see. This is 780 nanometers. So the band gap of silicon should sit right about. Oops, sorry. Does work a little bit right about here. And so essentially can absorb all of this light that's down here, whereas all of this light up here is wasted and can't be absorbed. Okay, so what about the structure of a solar cell? So this is essentially what a solar cell looks like. Typically it's built up of a p-n junction. And what happens is that we come in with light from the top, the photon is absorbed, where are we here? Photon is absorbed and we create an electron-hole pair. The electron-hole pair is then separated at the p-n junction that we have. So there's this interface here between the dark blue and the light blue. And once we separate them, then they drift to the electrodes because we have an electric field in there. So the electron to the top electrode and the hole to the bottom electrode, and that essentially creates current. Okay, so as I said, the long wavelength light passes through the solar cell completely. So if it's below the band gap, then it can't be absorbed. And if it's slightly above the band gap, then essentially it takes a while for it actually to be absorbed. And so that's why typically for a solar cell, you need to have an absorber layer that's about 200 microns thick. So that's about 4 times the thickness of a human hair. It doesn't actually sound very thick. All right, there are other loss mechanisms that go into this. For example, we have top electrodes. You can see this is a metal finger electrode. Obviously, metal can reflect light, so we can lose light in this case here as well. And that brings me to one of the most important plots that you have for solar cells. Essentially, a couple of gentlemen named Shockley and Queisser looked at how much of the light can you actually use that's coming into a solar cell, how much of it can actually be produced. And that's what's shown in this graph, essentially looking at the percent of the incident light energy versus the band gap of the solar cell material that you have there. And if you look at the different regimes where you have there, all of these here, so as you're increasing the band gap of the energy, more and more of these photons can't be absorbed, and so they're all going to be wasted. Any photon that has energy that's larger than the band gap essentially still only produces one electron-hole pair, and all the other energy that goes above that is also wasted because the charge carriers just relax down to the band edges. So that all of this area is already wasted then. And as I said, then there we have top contact reflection, we have interface issues, and so those add up to the other losses. And so out of this entire square, this is the only usable electric power that you actually have from a solar cell for a single junction, which maximizes out to about 33% if you have an optimal band gap of about 1.3 electron volts, so about 900 nanometers, so also easily into the NIR, and so the near infrared region. Okay, so let's look at some of these materials that we have out there. So silicon, crystalline silicon is this red one here. It's about 1100 nanometers, something that goes out here. And what we're showing here is the absorption coefficient, so how thick a material needs to be to actually absorb the light. And you can see that there are a lot of materials that have different band gaps, so they're shifted possibly further to the blue part, to the visible part of the spectrum. But you can see quite quickly that they have absorption coefficients that are much, much larger than silicon. That means they absorb much, much more intensity. And it's actually done in a logarithmic plot, so essentially one of these then is a factor of 10. And so you can see quite easily that soon then these materials absorb 100 times as much energy as much light as silicon does. Also, another problem with silicon is that the band gap's not optimal. I said 1.3 is actually optimal for that. Silicon is slightly off that. And so you can see this is where silicon sits. So this is that top curve from the black curve that I showed you before, essentially limiting it. And you can see silicon's not exactly at that optimum point, but close to it. And some of these other materials that sit at different points along with their band gaps are actually very, very close to the actual maximum efficiency that's achievable. Okay. So if any of you have seen us talk on solar cells, you'll have seen this graph. This is one thing that research scientists making solar cells like to boast with, and essentially it's the best research cell efficiencies that are out there that are produced, that have been certified versus time. Started out from 1976, I think. That was the first year where they started out these different technologies, and all the different colors and icons represent different technologies. And so silicon is, this one here is a simple silicon single crystal junction. You can see that it's been gradually increasing from 12, 13%, slowly up to a value of 26.6% nowadays. So it's been steadily improving over the last 40 years or so. But one of the materials that's now gotten us excited, or gotten the field excited, is the Halidperowskites, which somehow this was shifted. I don't know how this happened. Okay, anyway, I tried to increase it nowadays, is actually this yellow and red curve that's sitting out here. So it started out in around about 2011, the first certified solar cell, and you can see that it's been increasing much, much faster than all of these other technologies. It's quickly overtaken some, now is up to a value of about 24.2%. This is only within about 7 years that it's actually been able to do that. So essentially, it's been able to improve as much as silicon has in 40 years in only about a fifth of the time. Okay. All right, so what is perovskite? Well, perovskite actually is calcium titanate. So it's a single mineral, the chemical structure calcium titanium trioxide, and it was discovered in 1839 by a German, Gustav Rose, and named after his sponsor, his benefactor, Count von Perowskite, in 1839, and so that's why that was called perovskite. But basically nowadays, all the minerals with the same crystal structure of calcium titanate are dubbed perovskites. So they have this sort of ABX3 crystal structure. Okay, so I said the material is an old dog. 1839 was discovered. 1892 was actually the first scientific research paper, interesting also by a German, by Dr. Wells on this. But then it took nearly 80 years, or a little over 80 years, until actually anything really happened with that. And that was when, again, another German, Dieter Weber, actually managed to understand the crystal structure that was using X-ray diffraction to figure out how this material was actually composed and then built up, to understand how the compositions actually changed the crystal structure in there. And then in the 90s, that was the first instance where it was actually used for anything optoelectronic. There was a group by Sherry Kagan and David Mitzi who used it for field effect transistors. But he actually says nowadays he doesn't know why he never came up with the idea of using it for solar cells. So he's kind of disappointed about that. 2009 was then the first demonstration of a solar cell using a so-called dye-sensitized solar cell, where the perovskite essentially is just an absorber material to pass the electrons and holes then onto a charge transport layer. 4% efficiency. The problem with the solar cells, the electrolyte that they needed to transfer the electrons and holes was made up of an aqueous solution, and perovskites tend to degrade in water, so the solar cell lived for about 30 seconds before it died. So that's why it took about 2 or 3 years then for people to figure out that this was actually a super material, because it degraded quite quickly. And they replaced this aqueous solution with a fully solid state solar cell. So 2012 then was a breakthrough when they actually were able to do this. And the efficiency jumped up to 12% relatively quickly. Within only 3 years of development, it hit 20%. And so currently nowadays, we're at a value then of 24.2%, as I said earlier. All right. So the crystal structure, I said ABX3. I'm just going to run through this in detail, but basically we're sort of confined in what we can use as materials, because we have to preserve charge neutrality. So the oxide materials that I'm not going to get into are used for all sorts of things, like piezoelectric devices, for nanopositioners, for example. But the case that we're interested in, the halides, and the halides have a single negative charge, so essentially we need to balance them with these A and B cations, and so we're left only with a combination of the A being a single positive and the B being a double positive. Nevertheless, all of these materials can actually be used to make these halide perovskites, or can and have been used to make the halide perovskites. Although, essentially, another thing that we need to look into is the size of the ions. So obviously, you can see this crystal structure. They can't be arbitrarily large. This A cation that's sitting here in the octahedral void obviously can't be large enough, otherwise it won't fit in there. And so we're left up with a certain other restrictions there. 2 factors that essentially just take into account the radii of these materials, the Goldschmidt factor and the octahedral factor, that basically give us a range of tolerance factors for where these perovskites can exist. And so there's essentially just plotting then these 2 factors versus each other with a predicted range where all of these materials are stable. And you can see it's only more or less a very arbitrary number, as there's some materials that sit in this region that perovskites shouldn't exist that do, and the other way around. We also have materials that should exist that don't. So it's sort of a very arbitrary science in which of these materials actually work and form stable perovskites. Okay, so the materials that have gotten the world really interested now actually don't only contain single ions, but contain organic molecules that are sitting here. These actually sit here in the octahedral voids in these A spaces, so there's methylammonium and formamidinium. These are about basically the only real molecules that can actually fit in these spaces. Anything slightly larger than that wouldn't fit in there. You can see again here fitting on the tolerance factor versus octahedral factor. So these different combinations fit nicely into there with the different halides, the chloride, the bromide, and the iodide, and the different acid ions sitting in there. Okay. So now that we know the composition and the structure, we need to figure out how the electronic and the optoelectronic properties come to be. And essentially what we see is they're mainly governed by the inorganic framework. So the energetic bands, I talked a little bit earlier about the conduction band and the valence band. They're essentially given by the electronic orbitals of the lead and the iodide itself. And what makes the perovskites really interesting is that if you exchange now the halides, which are in different rows in the periodic table, you can get a very efficient bandgap tuning just by tuning the composition of these. So essentially what you're doing is you're shifting the position of this bottom valence band with respect to the conduction band, and so you're able to tune your bandgap from somewhere in the NIR out to nearly the ultraviolet range. And so now if you're looking at these are actual solar cells and the absorption spectra of these and varying the composition from purely iodide to purely bromide, you can see a very nice tuning capability throughout a very, very large range of the perovskite. All right, so I said that the absorption in perovskite is about 10 to 100 times as high as in silicon. So it's actually, or not for perovskite itself, but for other materials. But perovskite is also very, very efficient at absorbing. And that means that the absorber layer can be a lot thinner in the perovskite itself. And so if you look at the cross-section, this is taken in scanning electron microscopy, this cross-section of a solar cell. Essentially, you have an absorber layer of the perovskite now that's only about 300 nanometers thick. So again, in fact, about a factor of 1,000 thinner than for silicon. So that means you need a lot less material, and you can also come up with interesting applications that I'll get into a little bit later. All right, and so basically just to build up the solar cell again, we have the perovskite in the middle. We need electron transporters and hole transporters. They basically make sure that the electrons go into one direction, the holes go into the other direction. We have top and bottom contacts, and that then creates our current and our voltage in there. All right. So that's what a final perovskite absorber layer looks like, made out of methylammonium lead iodide. So you can see it's a very deep brown, so it's absorbing most of the light that comes through the visible spectrum, and that's what the final perovskite solar cell looks like. All right. What are the advantages of perovskite solar cells? Well, first of all, you can shift the band gap to the optimal position, so you get a higher theoretical maximum efficiency, so about 33% with respect to silicon, which can only achieve 29. You can get a lot thinner layers, and the materials that you need for that are abundant and cheap, and this is a lot easier to do than for silicon. And more, very importantly, you have tunable band gaps. All right, so why is a thin layer actually interesting? So basically, now you don't need to have a very rigid substrate to be able to hold all of this load, but you can actually start to use flexible substrates. That means you can do roll-to-roll printing, where essentially you have a polymer substrate that basically gets printed on just like people do with newspapers, if they are still printed nowadays. And so basically that makes the process a lot faster and a lot cheaper. You can make things like mobile chargers, where basically you can roll them up and then unfold them then to charge anything up, any devices up in the field. They're not bulky anymore. You can think about using wearable electronics. That's especially something that the military in the US is very interested in having their soldiers then basically with electricity in the deserts for any of their devices that they need there. Or solar-powered vehicles, obviously. You don't want anything heavy and bulky sitting on top of your car, then basically that you always have to lug around and move. And so I think last year one of these planes actually broke a record for the amount of duration that it could fly around the Earth. I think it was something like about 3 months that it was in the air continuously without having to recharge. All right. Another advantage is that you can integrate these into building architectures. So for example, you can create semi-transparent windows to absorb some of the light, so to use a lot of this area then, not only the roofs, but now also the windows, for producing electricity. Now the problem, or one of the problems is, I showed you before the absorber layer, it's brown and potentially ugly, so not necessarily everybody wants to have these coating their windows. And so one of the ideas that somebody came up with was actually producing color-neutral windows. And the way that they did this was, instead of making a thin film of perovskite, a continuous film, they actually developed islands. And through this sort of island formation there, what they were able to do is to change the absorption from deep to basically just only partial. And so the absorption spectrum itself is nearly flat throughout the entire visible range. So instead of having a dark brown, you essentially just have a sort of gray. Obviously, it reduces the efficiency to only about 5 to 10%, but if you think about the areas that you have on buildings for windows, especially skyscrapers or something like that, you have huge areas available, and so that can more than compensate the loss in efficiency. Another idea is to use so-called smart windows. So there's a material, also a perovskite here, where a material can be switched between an absorbing and a non-absorbing state. And the important thing here was that this was essentially done through by a phase transition, so the transition between two different configurations of this crystal. So this is the normal perovskite form that you can see, and this is a so-called 0D state. And this is actually achievable only through heating from sunlight. So this perovskite itself can absorb light. It goes into an absorptive state, and then essentially can be used as a smart window, for example, during the day. If it's too bright, then it can dim the light that's coming from the inside, so sort of like a pair of photochromic sunglasses. All right. That was thin layers. Additional thing that I want to look at is the tunable band gaps, because now you can, if you have band gaps tunable, you can begin to think about tandem solar cells. So tandem solar cells, I told you the idea essentially that in the single junction solar cell we can only really use a small part of the light, because either the photons have not enough energy and aren't absorbed, or they have too much energy and all of this is lost due to thermalization. But you can actually overcome that with a strategy that if you, instead of using a single absorber layer, you actually start to use multiple absorber layers that are tuned to different parts of the solar spectrum, because now they can absorb a different amount of light and transfer a different amount of this energy actually into usable electric energy. And so now if you look at the actual efficiency, the theoretical maximum efficiency, so for a single junction I said was 33%. As you increase the amount of junctions using only a second absorber material, you're already at about 50% of the light. And then it increases on until technically if you have infinity junctions stacked on top of each other, you could absorb 87% of all the light. Obviously it's not quite feasible to actually do this. All right, so has this been done? It has been, and so in using only pure perovskites, because you can tune the band gap of these perovskites, you can actually set them up to the optimal configuration. So What's shown here is a theoretical calculation of the bandgap energy of the bottom cell versus the top cell, and in the color-coded is the maximum efficiency that you can achieve. So 46% is the top in red, 0 in dark blue, and you can see there's sort of a relatively large area here that you can tune the band gaps within, so about 1.2 and 1.7 I think is the optimal value. So these are on the border of the NIR region, and you can very nicely replace part of these components in perovskite to basically tune the absorption throughout the entire necessary wavelength range to get this. There are two different configurations. I'm not going to go into too much detail on this. Essentially, 2-terminal and 4-terminal contacts that can be done, where essentially this is the 4-terminal is essentially two separate solar cells that are just stacked on top of each other to work independently of each other. It's a lot easier to produce, although it has more layers and is more expensive, so it's not the optimal. And that's why people are trying to go towards the 2-terminal variant of these solar cells. And so this is again another cross-section of one of these tandem perovskite solar cells, with the top layer absorbing at 1.2, the bottom at 1.8, and you can again see here this scale bar is 500 nanometers, so this entire thing is very, very thin. And efficiencies they showed there are still below what you can actually get in single junction perovskite, so you can see that while theoretically it's quite easy to do, it's very, very difficult to actually match all of these energies to get all of these layers nicely consistent and sitting on top of each other. So it's definitely something that people are working on right now. All right. But possibly easier to achieve and quicker to commercialize are perovskite silicon hybrids. I mean, silicon's already been established for 40 years and is working quite efficiently. And so the idea is, why not make use of this highly efficient silicon PV technology and just put a second perovskite on top to absorb some of the light that the silicon can't use as efficiently. And so that's also possible in the 2- and 4-terminal geometries, so having the perovskite to absorb light, only some of them passes through into the silicon. Then at the bottom, and that's again another one of these plots, just looking at whether for which energy you need. So essentially, because the band gap of silicon is fixed, now you have to that sets then the optimal range of the perovskite. So about 1.7, slightly shifted from the other case, but it is doable. And so nowadays there's a company that sits in Oxford, founded by Henry Snaith, Oxford PV they're called. They bought up one of the failed German solar cell companies. That has a production system in Brandenburg, I think it is, and basically now they're already industrially producing these silicon solar cells. So these are it says 16 by 16, should be a little bit larger. It's about I think 6 by 6 inches. No, that's about the same right size. That are 20 to 22% efficient. So actually very, very efficient silicon solar cells. And what they're doing now is just putting a perovskite solar cell on top of that, there to make the joint perovskite silicon hybrid solar cell, where technically they should be able to reach 30% efficiency. Sorry for the spelling error. Cross-section again of this cell, so this is only the top of the silicon layer, then you have a little layer in between to passivate it and also for extracting charges, and then the perovskite sitting on top of it, and then a transparent conductive electrode sitting on the top. And this is what one of their cells looks like, and they currently hold the record for a tandem solar cell, which is at 28%. And I listened to a talk by their CTO in April, and he said that by the end of the year they expect to be selling these things commercially already. So it's already quite efficient, and essentially the cost of adding this perovskite layer on top is really not a non-factor with respect to the overall cost of the total module of these systems. All right. So obviously one way of getting around our energy problems is by getting alternative light sources, but a second method is by enhancing energy efficiency. So cartoon looking at essentially an old light bulb we hardly use anymore, replaced then with the CTE bulbs that we had there, and nowadays basically all that's installed anymore is LEDs. And so perovskites itself are ideally suited for light emission. Basically, we talked about that before, showing that as you tune the band gap, you can tune the absorption, but you can also tune the emission of these. So they can emit anywhere between the blue and the red. And actually, if you go into making nanocrystals out of these, it turns out that they're extremely efficient in how well they produce energy. So essentially, if they absorb a UV photon and then with yields of nearly 100% convert this then into a photon of a different energy in this case. And so obviously, you can mix this up now to make very nice LEDs. Okay, What is an LED? And an LED is essentially just a solar cell that you drive in reverse. So technically, if you actually, you can use a solar cell and put the voltage on the wrong way around, and you actually get light out of that. You won't be able to see anything, obviously, because it's silicon, and so it emits in the infrared. But it's essentially the same principle. It's just that now you're taking electrons in holes and injecting them, so you're going the wrong way around because you have a current. They are able to overcome these energies, and then they reach the middle of the perovskite layer, in this case, and recombine. The electron falls down into the conduction, into the valence band, and produces a photon. So the first perovskite LEDs were demonstrated in 2015. These are only very, very small ones, but emitting in the red and green. A different case where you can show now you can actually do mixed cases. So basically now you can tune this throughout the entire visible range. And efficiencies, at least in the red and green, are already about 20–25%, which is very good for solid-state lighting applications. Okay, so question, are white light LEDs possible? So first of all, what you need to know is what are we looking for if we have white light? So obviously, technically, white light is, or this is a daylight spectrum. You can see it's a relatively flat spectrum that's coming from the sun, more or less. But if you're absorbing, or if you're looking at your eyes, essentially we don't absorb light equally. But we have basically three different components. We have three photoreceptors that are sensitive to individual wavelengths that absorb in the blue, the green, and the red. And their absorption then makes up all these different colors that we can actually see in our eye. So essentially all we need to do is tune the emission to these different wavelengths, and then we're able to get an LED that looks as white as possible. So basically getting a red, a blue, and a green LED together to make a white light LED. One of the big problems, though, is there's essentially no efficient material that actually produces green LEDs. And this is a huge problem. This is also known as the big green gap, as defined here. So nitride LEDs are basically what drove the white light LED production itself. Phosphide LEDs, other materials in the red, are very efficient as well. But there's no semiconductor material currently that can actually overcome this. And this is where perovskites then actually come in. But typically, so how people get around this is they make a blue LED, so a nitride-based LED, have a yellow absorber and emitter on top of that absorbs some of this blue light and confines or emits it. And basically what you're doing is you're tuning the amount of blue light that's still coming through with the yellow light that's produced by this phosphor, and that gives them the different color spectra that we can see there. And that's what we're calling then warm white and cool white or daylight, or all these different types of white scales. Essentially, all we're doing there is a change in the blue to yellow ratio, and that changes then the apparent light or the whiteness of this light that we're getting out. Okay, so what about for perovskite LEDs? I mean, you have different strategies that go out there. So again, you can emulate the same strategy that we have currently so far, where you have a blue LED and you bring on a yellow emitter. So this is an emitter where a process known as self-trapped excitons actually creates a very, very broad emission state in the yellow, and that produces essentially white light. So that's feasible with perovskites. You can also then tune the perovskites to be red and green emitters, absorbing the blue light to get white light out of there. There are also people that have made LEDs there. So essentially this is the light from the blue LED that's on the back, and then the green and the red perovskites add up to make white light. Going further, basically producing something in the UV so that essentially all of the emitters are now perovskites. So you have a blue and a green and a red perovskite adding up to make white light as well, as you do in a TV, a typical. But ideally what one would like is to have a blue, a green, and a red LED that are driven directly by electricity or electric current and don't actually have to absorb any light and then re-emit it again, because that is obviously not always 100% efficient. So that's essentially what a simulated spectrum of such a thing would actually look like. Okay. So there's still a couple of limitations. So perovskite's not all perfect. There are a lot of things that currently impede widespread commercialization. So one of the big problems, especially in Europe, is that it contains lead. At least most of the efficient perovskites contain lead, and the European Union does not like lead at all. So that's one of the big problems for putting into TVs or putting into solar cells. Although if you actually covered the entire land mass with perovskite solar cells and had them leak out completely into the ground, you wouldn't be able to detect any of the lead behind the background contamination that you have of lead anyway. Nevertheless, the European Union doesn't like lead. So what people are trying to do to replace lead is to look at the periodic table. Okay, lead sits here, this yellow component over there. Why don't we stay in the same period, use tin or germanium, because they're essentially chemically more or less the same. The problem is the stability, because tin and germanium like to form 4+ states instead of 2+ states, and they act as then traps then for electrons in holes. So essentially once they're created, they then tend to get lost and not be able to be used for electricity. And so an alternative strategy that people have come up with is, okay, so we looked at tin and germanium for staying in charge neutrality, but why not go one to the left and one to the right and combine those together, because one is a 2+, one is a 4+, and so essentially you come up with a 3+ case. So using tantalum and bismuth, essentially, and that's where people have started to develop these so-called double perovskites, because essentially the crystal structure is double as large. One of the big problems there is bismuth is actually even more toxic than lead is. But there are also other strategies where people then have gone into the transition metals, looking to silver, for example. I think one of them is cesium silver and something else that they're using in there. So a lot of material space then to possibly overcome this toxicity issue. All right, another big problem that I said, or that we have. Oh, great! I have lots of time left. So red and green perovskites are quite efficient. They actually produce extremely bright LEDs, so I think 23, 24% or something about the maximum. One of the big problems is that blue perovskites are much less efficient. So this is essentially just two dispersions of blue perovskite nanocrystals in there, and you can see the quantum yields are only about 6 and 22%, so that means the amount of photons absorbed by the light and then actually producing blue photons. So it's a lot less efficient. And so obviously if you want to have an all perovskite LED, you'd like to have blue, green, and red coming together. Another big problem is environmental stress. So I told you about the first solar cell that was built into an aqueous environment and disintegrated within about 30 seconds. That's also a big problem for solar cells, because if you have a solar cell sitting anywhere, it's going to heat up, it's going to cool, it's going to expand, it's going to contract, and that then is perfect for letting water in, and that lets then solar cells degrade quite quickly. You can see here the nice black absorber, meaning essentially all the light is absorbed. Relatively quickly, it becomes more and more yellow as this perovskite disintegrates back down to one of the original components, the lead iodide. So that's one of the big problems that people are then looking into encapsulation. Another problem that I'm not going to get into in too much detail is that I told you can mix the halide composition quite nicely to get individual emission colors in there. And one of the problems, though, is that despite the perovskite being more or less semiconductor-like and having a nice crystal structure, is these ions don't actually like to sit necessarily at the same spot that they're put in. So if you put on an electric field, which you need quite large in LEDs, a couple of volts in there, what happens is that these ions then start to migrate, to go to different areas. So in this case, where you have bromide and iodide, they form then regions that are bromide-rich, regions that are iodide-rich, and as you know from semiconductor physics, then the electrons and holes always want to go to the energetic minimum, and so they're going to go towards the iodide-rich regions, and so essentially what's going to happen is the color of your LED changes as you're running it, which is obviously not ideal. All right, so some of the work that we've been doing on is aimed to attack some of these strategies. So we've been mainly looking at overcoming some of these blue issues and also looking at stability of these nanocrystals. And so what we've been doing is when the first nanocrystal was actually produced in 2014, we wanted to understand how the synthesis mechanism worked. And so essentially what you get we copied one of the first paper that was out there, produced these nice bulk nanocubes. I think the scale bar is 200 nanometers in this case. You can see these nice cubes sitting in there. And they were using long organic ligands to passivate the nanocrystals. And so what we found is that as we added these organic ligands, instead of the crystals getting smaller and smaller, what we were doing is we're transferring these cubes into quantum-confined nanoplatelets, very, very thin nanoplatelets. And to look at how this affected it, essentially what we're doing is we're starting out from these bulk cubes and then adding a percentage of the organic ligands in there. And as you can see, as the content goes larger and larger, you can see the color of these actually shifts. And from TM images here, you can see it's thinner and thinner. And so essentially we're going down to very, very thin nanoplatelets. And in this case, actually, of the 100% organic ligand, what we're seeing there is actually a single monolayer, which in this case is only about 0.6 nanometers thick. So extremely thin layers out of here. All right, why is this in here again? Interesting, okay, sorry about that. Problem with the nanoplatelets that we had in this case is a thickness control. So if you look at the spectra in there, you can see that they're not nice, ideal single emission spectra, but they're actually quite large and bulky. And that's due to the fact that we don't only have a single thickness in here, but we have different thicknesses, and each of these have a slightly different absorption and emission spectrum. And so that leads to these broad spectra that we're seeing in there. And also the efficiency in the blue is quite low, and the stability on substrates was quite weak. And so there we replaced then the organic ligand organic molecule with cesium, And now we were able to control the precursor ratios a lot nicer. And as you can see here, again, we were able to do this fine tuning of the colors, but you can see the spectra are only single peaks there and actually quite narrow in this case. And if you look at electron microscopy images of the nanocrystals in here, you can see these are all nanoplatelets with a single thickness of 5 monolayers. In this case here, you can see they're slightly thinner. These all have 3 monolayers. And essentially what we're able to do is control then now the thickness of these platelets with a single monolayer position, so from 2 monolayers, so just over a nanometer, to a little larger, to cubes, and so can really nicely tune now the emission color of these nanocrystals. Again, the quantum yields, though, suffer from that. So the cubes that we're able to produce have a quantum yield of about 95%. As you can see, as we go thinner and thinner and thinner, they become worse and worse. And what we found, though, is that we could actually produce, or we can enhance the efficiency of these by adding a second step in the synthesis, by basically adding an extra amount of lead bromide to this. And so we're going from very, very low values on the order of about 5 or 6% for these thin cases to values that are over 50 or 60% in the deep blue. And what we found is that the enhancement factor, so the factor by which the PL quantum yield goes up, is larger the thinner it is. So we immediately thought of the idea, okay, this has to have something to do with the surfaces that we have in there. And so essentially what we're saying is that at the beginning we have a lot of platelets or some platelets that absorb light and make photons. These are bright platelets. We have a lot of dark ones that absorb light, but basically the light is trapped. It can't come out of that again. And what this lead bromide is doing is essentially, in these dark platelets, we have a lot of imperfect crystals there, and it's basically filling out these holes that we have in there, filling out the crystals so that they then turn into nice, fully passivated crystals, and that's then turning a lot of these dark platelets then on again, that they now are able to emit light efficiently. And so in a collaboration that we had then with a group at Cambridge University, we were able to produce a blue LED. You can see in an extremely narrow spectrum. So essentially all the light is focused into one small range. That got us really excited. If you ask me about the quantum efficiency of this device, it's at that time it was the 3rd best perovskite blue solar cell in the world with an EQE of 0.06%. So nothing to write home about. Something you can definitely publish, but nothing to go in there. And there are a lot of issues that are still on that sense. And so we figured out, okay, it's not only the quantum yield that we need to go into, that we need to take care of, but we need to also look at the actual device structure. So I'm not going to go into too much detail, but one of the big problems here is that as we're injecting charge carriers, there's a huge drop-off from the whole transporting layer into the perovskite, where it's really, really difficult to actually get these holes to go into the emitter layer. And so they're essentially sitting right here at this interface and recombining non-radiatively. So we've been working on then adding additional layers into there to enhance the efficiency of these devices. And that was a follow-up paper. I forgot to change that. Was accepted actually just a short while ago, where now we are able to produce 2 different blue LEDs now with values approaching nearly nearly 1% EQE, so a lot better than before. But again, you can still see that are far, far behind anything that the blue and the green perovskites are in. All right, how am I for time? A couple of minutes. Okay, I'm just going to run through the end. This is something that I'm really excited about, that we've been starting up now with our new group, essentially to look into the passivation of these perovskites. And so now we start up with a new synthesis method, but instead of adding organic ligands to the solution to passivate the crystals as they grow, instead what we're doing is we're preforming block polymer micelles. So these are polymers that consist of 2 different parts and thus have a different effect in the surrounding ligand, surrounding medium, and so form these micelles. And what we get to happen is then we add the perovskite precursors to the solution. They don't like to be out in the solvent, but like to diffuse into the cores of these micelles, where they then form perovskite nanocrystals there. And we can then take them together, form really, really nice monolayers on substrates, and start to look at their actual properties. So you can see here, this is a TM image now of a field of perovskite, of these micellar encapsulated nanocrystals. They're very small. These are on the order of only about 4 nanometers. AFM studies show that they're very, very homogeneous. So we have a surface coverage here in this case of about 99.8%. So you can make very, very nice layers for that. You can tune the emission energies throughout the full range of the visible spectrum. So basically the same as you can do with their other nanocrystals. You can do size tuning in them, which is important then also for getting into quantum confinement effects. But more importantly, they're stable or more stable to water. So if you look at just typical nanocrystals there, again, they degrade relatively quickly. These are just nanocrystals made without any of this polymer, and so within a couple of days, the total photoluminescence that's coming out of them vanishes down to 0. In the case of our thin films, basically we can have them sitting out in a sample, and we can even put water on top of them, and they don't change the spectrum at all. And now if you monitor the total photoluminescence intensity over time, you can see this here, this black curve is essentially one of these nanocrystals, so it drops off. This is them sitting out in air. After about 13 days, you can't see anything anymore. In comparison, this green curve is what we now have in these perovskites sitting out in air. We've now reached over 400 days, and they're still efficient at about 40%, so a factor of about 40 longer. And what's actually gotten us even more excited is this blue curve. You can still see a drop-off, but essentially what you have to know is that this is a film of these perovskites that's sitting in a glass of water. And it's been sitting there for 75, 80 days, and it still emits light afterwards. So obviously it's not perfect, but it's a lot faster and a lot more stable than any of the perovskites that we have nowadays. All right, and with that then, I'd like to sum up briefly. Sorry about the colors here, it looks better on the screen. So essentially, perovskite, an old material that's been rediscovered and used for different applications. It's based on the extremely good optical properties, including absorption and tunability of the band gap. Because of these properties and the thin layers you can do, you can have lots of different applications ranging from solar cells to LEDs and also others that I didn't talk about. Obviously, there's still some problems left. Toxicity, degradation are still problems in the blue emission. But interest is constantly growing. So if you just look at, this is recently from Google Scholar, the amount of papers that are being published over years on the field of perovskites is increasing steadily. So I think last year there's something on the order of about 10,000 papers that were produced on perovskites. So even we can't keep up with everything that's being brought out there. And so the future of perovskites, I would say, is quite bright. And with that, I'd just like to thank all the people that have done work on this. So my former group, the chair for photonics and optoelectronics here at the LMU, my new group, which is now already twice the size of this. This was in Oktoberfest last year, so when we started up in August, and collaborators that we have at the TUM, Antwerp and Cambridge, and then all of my funding sources. And then I'd also like to thank you very much for your attention.